Okay. So, we will take a few problems which are itself an interesting problem. In itself is a very interesting problem, and also it involves some other concepts in connection with the sets. So, let us see the first problem. Define the Cantor set. Cantor set and show that and prove the following say now 1 or A part, the Cantor set is closed set. Cantor set is a closed set. Second, we wanted to show that Cantor set contains no non-empty open interval. Cantor set contains contains no non-empty non-empty open interval as subset, as a subset. As third point, which we want to prove that Cantor set is an uncountable set. Cantor set, the length of the Cantor set, you can say the Cantor set has a length, the total length of the Cantor set, total length of the Cantor set, you can say Cantor set is 0. In fact, the measure of the Cantor set is 0. We wanted to show this is the length, or we will say the measure is 0. The measure of the Cantor set, instead of saying total length, we will just say the measure of Cantor set is 0. Cantor set is having length 0. Okay. And D, the measure of the Cantor set, I will because we have not discussed the measure, that is why I wanted to avoid this term measure. Okay. And then fourth one is Cantor set. Cantor set is an uncountable set, is uncountable. So, we wanted to establish these following 4 things about the Cantor sets. Let us see the solution. So, first let us define the Cantor set. So, what is the Cantor sets? The construction of Cantor set. Let us consider a closed interval 0 1. Divide this interval into 3 parts, 1/3, 2/3, and then remove the open interval and remove the open interval, middle one, open interval, 1/3 open middle interval, 1/3 2/3. So, closed interval 0 1, we are dividing first into 3 parts and removing this middle portion or the middle open interval we are removing. So, the set which obtained, so we get a set, let it be denoted by F2 or say F1, as the remaining set will be 0, 1/3 closed interval union of 2/3 1. So, in the first step, what we are doing? We are taking a closed interval 0 1 and from there we are dropping the middle portion, this portions we have dropped. So, the remaining one will be this interval 0 1/3 and then 2/3 1. Okay. This is our remaining interval and this we said denoted by f 1. Now, what we are doing is now we next again subdivide these intervals this one into 3 parts and let it be divided by this interval again in 3 parts, this interval also again in 3 parts and then from here we drop this one, we drop this portion, this middle open portions. So, what we do is we next remove the second step is we next remove the open middle interval, remove the open middle third middle third of each of middle third, we open middle third of each of the two closed intervals in f 1. Means we are dividing further these remaining intervals into 3 parts and then out of these 3 intervals we are removing the middle one open intervals and to get that set to obtain the set say which we denoted by f 2 as 0 1/9 union 2/9 1/3 union 2/3 7/9 union 8/9 1. Okay, that is what. So, basically this is if we have it this structure, suppose I have 0 1, then what we do first we are removing this is say 0 1/9 2/9 2/9 3/9 that is 1/3 1/9 2/9 3/9 let it be, then 4/9 5/9 6/9 and then 7/9 8/9. So, these are them. So, what the remaining portions was earlier we have already removed 1/3 2/3, this portion was already dropped, is it not? This portion was already dropped, this was dropped. Then in this interval we are dropping this portion, we are dropping from here this portion. So, these portions are dropped. So, remaining portions will be this 0 1/9, okay. Then this portion is dropped. So, 2/3 and then 1/9 this portion, then this portion is dropped. So, here 6/9 means 2/3, then 7/9 and this portion is dropped. So, this one is then this one is 8/9 and 1. So, basically these intervals are there, closed intervals are left. Union of these we denote by f 2. Okay. Now, each of these f 2 we see that f 2 is the union of union of 2 to the power 2, that is 4 closed intervals, each of which each of which is of the form k over 3 square comma k plus 1 over 3 square, is it not? Because this is also k is 0. So, you are getting 0 and 1 by 3 square. When you are taking k is 2, you are getting this one, k is equal to I think this is 1 by 3, here is 1 by 3. Okay. So, 1 by 3. So, you are getting this one, and similarly, when you take this k is equal to 2, you are getting k equal to say 6, you are getting this one, k equal to 8, you are getting this one, like this. So, all these of this form, and then the length of this, if you look the basically the length of the first one, dropped one, which you have dropped. What is the length of the dropped interval? Is 1/3, and here and only one number of intervals we are dropping, number of interval which is dropped is 1. Now, here the number of intervals, number of length of these intervals, the number of intervals dropped is how many? 1 and 2, and length of each interval dropped interval will be what? Length of each dropped interval will be 1 by say 3 to the power p. So, each one will be of length say this one 1 by 3 square. So, that is the first interval, 2 intervals, each length of 1 by 3 square, 9 length we are dropping for this. Okay, like this. So, continue this way. So, if we continue this way, then what we will next remove? Step third, we next remove the open middle third thirds of each of these sets to get F3. To get F3, which is the union of two to the power 3, that is 8 closed intervals. And like this, we continue this way. So, what we get? That in the nth step, if we take then in nth step, then f n at the nth step has been constructed, has 2 to the power n intervals, closed intervals, of course, to the closed intervals of the form k over 3 to the power n, k plus 1 over 3 to the power n plus 1, like this, and then we obtain the set or then f n is the union of 2 to the power n intervals of the form this one. Then we obtained the set f 3, the set f n plus 1 by removing the middle again, by removing the open middle open middle third, open middle third of each of these intervals. And like this. See, then what is Cantor set? The Cantor set denoted by say capital F is the intersection of the sets f n when n is a integer, so set of natural number of positive integers obtained by successive removal of open third intervals, open thirds, open middle thirds, starting with the closed interval 0 1. So, this set F will be the Cantor set. So, basically the Cantor set will be the collection of all the end points of these removed intervals. So, in fact, we get, since it is a closed, so we know. So, basically this set is the collection of all the points which are the corner points of these deleted intervals. Okay. Now, we wanted to establish these results. The first result says the Cantor set is a closed set, which we want to show. So, now first is, since Cantor set F is the intersection of f n is 1 to infinity, a countable intersection of f n, and since each f n is closed, is a closed interval, is a union of closed intervals, is it not? And closed intervals, finite union of, is a finite union of closed intervals. So, each f n is closed, and when you take the countable intersection of the closed set, then it is closed. So, the countable intersection of f n 1 to infinity is closed. Hence, the Cantor set F is a closed set. So, this is the first we wanted to prove. Second one, we wanted to show that Cantor set contains no non-empty intervals as a subset, and then length of these Cantor set or measure of the set is 0. Okay. So, suppose what is our B part? The total length of f n. The total length of f n is basically what? Is nothing but the 2 by 3 n, because if we look that one, the first one interval is of length, when you choose the f 1, the f 1, this length is 1/3 plus 1/3. So, it is equal to 1/3 plus 1/3, that is 2 by 3. When n is 1, it is 2 by 3. When n is 2, the total length is coming to be this n is 2. So, what is this is? This is 1 by 9, 1 by 9, 1 by 9, 1 by the 4 intervals of length 1 by 9. So, it is 2 square by 3 square, that is when n is 2, it is 2 square by 3 square. So, 4 by 9. So, similarly, when f n comes, it length will be 2 by 3 power n. So, in general. Now, if suppose f contains, if f contains a, suppose f contains a non-empty open intervals say j of say a b, then f is the intersection of all these open intervals. So, obviously, f 1 covers f 2, cover f n and so on. So, basically we say this interval a b will be, so since j which is this open interval is contained in f n for all n, this is true, is it not? For all n j is contained in this. So, the corresponding, so we must have the length of this is b minus a, which is positive, must be less than or equal to the length of this f n, but as n tends to infinity, this right hand side of this goes to 0, the right hand side goes to 0. So, this implies that a is equal to b. It means, we do not get any intersection. So, j is empty, j is an empty set, empty, hence a contradiction, because what we assume that it f contains a non-empty open interval. So, which is not true, contradiction. Hence, the Cantor set will not contain any non-empty open interval as a subset. Now, third part is the measure of this Cantor set, is 0. In fact, I do not want to introduce measure. What is the measure? Suppose I take the interval a b, then when we say a b is interval, open interval, closed interval, the length of the interval is b minus a. So, that is called the measure of the interval. Okay. Similarly, when we say other set, when the set is there, then it is difficult to find out the interval, because if it says sets are scattered, then and lying in between the interval a b, then if you take b minus a, then the length of the set or the measure length is not exactly same, because it is more it will contain some more point which is not available in the set. So, in order to get the measure of this set, we introduce the concept of the measure in terms of the length, and in fact, when we say measure of the set, then this is the infimum of measure of a set A, means it is denoted by A. It is the infimum value of sigma, the length of the interval I n 1 to infinity, such that the countable union of I n covers A, where I n is a intervals, open interval or semi closed intervals, which covers I n. I n's are semi closed, all open intervals containing this. So, when you take the length of the interval is possible, find the sum and take the infimum over all such I n's, we get this infimum exists, then we say it is a measure. So, in nutshell or in the rough sense, we say measure of the interval is nothing but the length of the interval. Since the set A f, which is a Cantor set, contains the points, basically the points end points of the removed interval. So, what we want to show, the length of the total set is 0, the measure of this set is 0. So, let us see the total length of the removed interval. Okay. The Cantor set f is basically is obtained by dropping the middle the open middle thirds. When you divide the whole closed interval into the 3 parts and opening, and then middle third you are dropping. So, is obtained by dropping this one. So, remaining one is nothing but the Cantor set, when n is sufficiently large, is obtained by this, and for n is sufficiently large, middle third in successive middle third of this, is it not. So, that is what intersection of f n, that is the intersection of f n will be intersection of f n 1 to infinity, that will be the Cantor set, is it not, that is f, where f n's are the remaining one, and then take the intersection. So, when you drop the middle one, then what happens to this? In the first case f 1, the length of the dropped interval, that is 1/3, 2/3 is 1/3. In case of M2, the length of the dropped interval is 2/3 and number of the intervals is 1. Here the number of the intervals is 2. Then continue this. So, in case of f n, when you are taking the f n, then basically it is the length of the dropped interval will be 1/3 to the power n plus 1, 3 to the power n, this number is 1, sorry, this 1, and then each one is 1, and but the length will be f 2 3 square, sorry, 3 square, number is 2. So, here when it is say in that second case, the number of the interval will be 2 to the power n, like this. So, it is 1. So, the total length of the removed intervals is nothing but what? 1/3 plus 2 over 3 square plus 2 square by 3 cube and so on, plus 2 to the power n by 3 to the power n plus 1 and so on. Basically, this is equal to 1/3 sigma n is 0 to infinity 2 by 3 power n. Now, if I add, this is a geometric series. The geometric series, the first term is 1. So, it is 1/3 1 over a minus r, and the length is coming to be 1. So, it means when the closed interval is there, from the closed interval, the length of the closed interval from where we have started is 1, and the dropped interval is also having length 1, and the remaining one is the Cantor set. Therefore, the total length of the Cantor set is 0. The total length of the Cantor set is 0. That is measure of the set is 0. Is clear? Now, next the last one which we want to show is the D part. The Cantor set is uncountable. Is uncountable. Okay. As we seen, the Cantor set contains all of the endpoints, of the removed open interval intervals, and these points are of the form 2 to the power k over 3 to the power k n of 3 to the power n, where k is 0, 1, 2 up to say n for each n. The collection of these points is the Cantor set. We wanted to show this Cantor set is uncountable. Okay. So, these are infinite. First thing is the Cantor set is an infinite set, because there are so many points are available. So, it is an infinite set. Clearly, Cantor set is an infinite set. Okay. Infinite set. Now, let us take, if we take any point x belongs to the interval 0 to 1, then we can, since each point x belongs to a can be represented internally, that is with the base 3, with the base 3, and its expansion will be as expansion will be x equal to sigma n is 1 to infinity n over 3 to the power n, where each n is either 0 or 1 or 2. Any point in the closed interval 0 1, a real number, we can express it in the a decimal expansion, in that expansion, in the ternary expansion with the base 3 as well. So, we can write this form as a 1 by 3, a 2 by 3 square, a 3, and the where a 1, a 2, a n may be 0, 1 or 2. Okay. This will be the. Now, if x lies in one of the, it is observed, it is also observed that if x lies in one of the removed open intervals in one of the removed then at least then ans will be 1 for some n. For example, suppose I take the interval, the each point, suppose I take for example, each point in the interval 1/3 2/3. This is the dropped interval, has first term a 1 is 1. Similarly, the end points of the removed interval similarly. So, this is true for each x. It is observed that you can write it that each x that lies in one of the open interval has ans to be 1 for some n. This is true. Now, in the interval say end points, further the end points of the removed interval say 1/3 2/3 have two possible ternary expansion, have two possible ternary expansion, one having no ones and set other may be some ones or 2. For example, if I take this 1/3, the expansion of the 1/3 ternary will be 0.1 0 0 0 0 third. If I take the same one, then we can also put it in this form 0 2 2 2. If you approximate, you will get 1. So, one of these expansion will involve ones and others may not have a ones also. Okay. So, at least one will have no n's will not be 1. Okay. So, this one. So, what we want is now we choose that expansion. If we choose, and these are the endpoints are in the Cantor sets. So, now we choose the expansion, we choose the expansion of the points of Cantor set x, of expansion of the point say x of Cantor set in such a way such that its ternary expansions has no ones, okay. That is we wanted to have it, no ones. That is, the ternary expansion will involve n which may be either 0 or 2 for all n belongs to n in the ternary expansion of each point of points x belongs to Cantor set. This we are assuming. Okay. Now, define a mapping psi from the Cantor set F to say closed interval 0 1 as follows. If I take a point x whose ternary expansion will be 1 to infinity a n 3 to the power n. This is the ternary expansion, and what we are doing is we are taking the image of this under psi as the point whose binary representation is this a n by 2 divided by 2 to the power n. That is for each x belongs to a. That is what we are doing is, that is the image of this psi a 1, a 2, a n and so on in ternary expansion, sorry, and so on. This is a ternary expansion of this point in ternary expansion is nothing but the expansion of the same point in binary mode b 1, b 2, b n etcetera in binary 2, where v n's will be a n by 2 for all n belongs to n, for all n belongs to n. So, this is our means each point I am picking up from here, writing down is ternary expansion, and then image of this we are taking the image as a binary expansion of the same points, okay, binary expansion for this. Okay. So, what we are doing, this binary expansion will also be a point in 0 1. So, each point which is in F will have a point in the 0 1 which is in 0 1. So, this psi is a onto mapping, okay, from F to 0 1. Now, let us suppose the F is countable. Suppose F is countable, this Cantor set F is countable. So, if it is countable, then there exists a mapping say phi from F to n or n to F, 1 to 1 correspondence with the which is 1 1 correspondence onto 1 1 onto 1 1 mapping correspondence for this. So, there exists a psi which is 1 1 from this to this surjection mapping, okay. F is countable. So, there is surjection of 1 1 onto, okay, onto. So, if we combine this thing, it means when we combine this, then what you are getting is that the composite mapping, composition of phi and psi, this will a mapping which brings the n to 0 1 n to 0 1 as surjection. This is a surjection mapping onto mapping. So, if we assume F to be countable, then basically this implies that this is F and this are having the surjection. There is a mapping from F to 1 which is surjection 1 1 onto a onto mapping. So, once it is surjection, then since we have assumed F to be countable, so this implies that 0 1 is a countable set, as we assumed F is countable. F is countable. This is our assumption, but 0 1 is uncountable set. What 0 1 set of all real number in between the 0 1, that is continuum, is an uncountable set which we have already shown. So, our assumption is wrong. Therefore, this implies that Cantor set is uncountable, and that proves the results. Okay. So, this is what we now another examples which we want to show. Define the drive sets problem. Define drive set. Define drive set and so that the rational numbers in 0 1 drive sets and so that the rational numbers in the interval 0 1 is a set of second species So, let us see first what is the drive set and what is the species we mean. Drive set, if the set S is infinite set, then what we do is we can find out the limits of this. We can find out the limit of this set. Infinite set may have a many limit point or may not have a limit point also depending on the set. So, if the set is infinite set, there is a possibility of having the limit points. So, we define the drive set as follows. Okay. The set formed by the limiting points of the set S of the given infinite set is known as the drive set, because finite set does not have any limit point, that we have already seen. So, that is why we are taking drive set. So, suppose I take the set S which having say point half, minus 2/3, 3/4, minus 4/5 and so on. Now, the drive set n is denoted by S dash by S dash. So, let S be the, I will write like, let S be an infinite set, of points. Then the set formed by the limit points of the given infinite set S is known as the drive set and denoted by S dash. So, for example, if we take this one, then what are the drive set? 1/2, 3/4 etcetera, the limit point will be 1 and minus 2/3 my limit point will be minus 1. So, this is the drive set having this point. Now, in case if drive set S is itself an infinite set, then there is a possibility of having limit points of S dash, and then the collection of these limit points, of S dash is denoted by S double dash and is called and is known as the second derivative, second drive set of S. Continue this like this. So, suppose if we continue this, suppose we have, after proceeding n, we have the S n comes out to be finite. So, proceeding this way, continue. if S dash, this is the first drive set, S double dash is the second drive set, S n is the nth drive set of S. These are the drive sets of S, and if S n is having finite number of terms, and if S n, the nth drive set has finite number of points only, then we cannot go further. We cannot go further, that is, we are unable to get the limit point of S n, and then we stop it here. Then we say that set S, the set S, if it is the S is that set S contains in next, and it is a drive set, S is of order n, and is of first category, and is of first category, that is first species. On the other hand, if S n is again infinite set for large n, greater than, then S is said to be, large n means for every n, you can say, then S is said to be of second species. So, this is the way. So, for example, the set of rational number, if is the set of rational numbers in the interval 0 1, it is of second species. Why? Because the set of limit point of this is the set of rational in the all rationals in the interval 0 1, then set of all irrational will also be the limit point of this, and basically this is nothing but the interval 0 1 itself. So, continue this, we get every times the drive set is comes out to be the set itself, that is this possible to get the limit point of this. So, it is of second category. Okay. So, that is what we want. Now, then we next problems. So, that problem which we have defined the range, so the rational number is of second species. Okay. Then define the dense in itself, everywhere dense set, and dense set. With examples. So, let us see the solution for it. What is our definition for the dense in itself? So, let us see the solution. We define the dense in itself a set S is said to be dense in itself if every point of S is a limit point of S, If every point of S is a limit point of S, then we say that set is dense. So, in such a case, so if S is a dense set itself, then it is subset, then so S will always be subset of S dash, because every point of S is the limit point. So, it is the S dash will contain all the point of S, okay, S dash. Thus, for example, if we take the set S as a closed set S is the closed set, closed intervals, all may be open intervals, closed intervals, all may be open intervals. These are all dense in itself, then in itself. Okay. Then set of rational number, irrational number, and the set of irrational number, rational number, set of rational numbers in any interval is dense in itself, set of irrational numbers in any interval is dense in itself, and like this. Now, we define the everywhere dense set. A set S is said to be everywhere dense if every point of the interval I in which S is contained is a limiting point of S. Means what a set is said to be dense, everywhere dense, if the interval in which S is lies, every point of that interval in which S lies must be my limit point of S. For example, if we take this closed set, then for example, if we take the closed sets or closed interval, S is the closed interval 0 1, then this is everywhere dense, because the interval in which it lies will be that set closed interval. But if we take this one dense, but this is everywhere dense, okay, everywhere dense because the interval is. But if we take the set S as the union of these interval 0 1 and then 2 3, if this set, if I take collection of all point in between this, then this is dense in itself, because dense in itself means every point of this is a limit point, but is not everywhere dense. Why is not everywhere dense set? Because a interval 0 1 0 3 does not contain the point in between 1 and 2. So, it is not every point, okay, dense. Then a set is said to be dense set, and lastly dense, we say a set S is said to be dense, if between any 2 point, between any 2 points of S there is at least one other point of S, then it is a dense. For example, if we take the interval 2 3, this is our S, then this is dense set, because between any 2 points there is a point of the interval. But if we take this set, say 0 1 comma 2 3, this collection S is not dense, because between any 2 points we do not get one between 1 and 2, the point which is available here. So, that is what is dense. Okay. A set is nowhere dense set, a set S is said to be nowhere dense or non dense if there is no interval in which S is dense. S is dense. For example, if we take the set of rational numbers 1, 1 by 2, 1 by 3, this collection is nowhere dense, because we cannot get an interval in between these whichever. Thank you very much. Thanks.